Welcome to a podcast focusing on an introduction to the substitution method within the context of integration. So we have derivatives in play. These derivatives will follow shortly, but the basics of integration relative to some of the derivatives that we now understand, namely polynomial functions and trigonometric functions, will be explored. The references to substitution method show up in standard texts, as well as the so-called inspection method. So let's see the power of the so-called differential operators relative to working backwards with this anti-differentiation process. So given you've got dy dx is equal to what you see here, cosine of quantity 3x minus 2, let's find that the function itself looks like this, with plus c as a general constant of integration. Some of us might be able to already ascertain, well, if the derivative of sine is cosine, which it is, of course, then the integral of cosine takes you back. And the idea of if you were to differentiate this kind of form to try to achieve what it needs to be, then you would need to undo that chain rule component of the 3x minus 2, so that derivative of the piece inside is undone by the 1/3. So there is some language out there that says you can just sort of extend from here and by quote-unquote inspection generate the answer. Totally valid. But let's look at it more closely in terms of the process of substitution, which generally speaking is really very, very handy and powerful, especially when the form of the integral intensifies. You can split the operator, and then you can apply the antiderivative, if you will, to both sides. We've seen this before, that the antiderivative of the derivative with respect to y is, of course, just y. That's kind of one step forward, one step back. And as you focus on trying to integrate this, the piece that controls the problem is the 3x minus 2 component. So what if we were to bring a substitution element, namely, let's let u equal 3x minus 2. And then you can differentiate u with respect to x and pick up that it's 3. Split the operators here, so then du is equal to 3 dx, which would then imply, if you wanted to free up this dx differential operator, that it's actually 1/3 of du in terms of its value. So you have this direct substitution possibility now. So the cosine of 3x minus 2 dx, well, you've controlled that choice. That becomes the cosine of u. And this dx operator has to leave the system because you're no longer integrating with respect to x. You're going to be integrating with respect to u. So dx is actually equal to 1/3 of du. You can safely pull a constant through the symbol of integration, and then you can clearly see that the integral of cosine of u du is, of course, just sine u, and you've picked up that 1/3 in the process. Not surprisingly, you add the plus c as that generalized constant of integration by so-called back substitution. By letting u be what it's supposed to be, we generate the answer. So you might argue, well, that's a long way to go. However, I think as we further proceed with the topic of integration, and more specifically integration by substitution, you might see that this kind of way to go is actually much more advantageous. Excuse me. So let's look at a related concept in a polynomial world. So given that integral here, let's try to come up with these parameters, p and q, and r for that matter as well. So given we can actually establish that the integral of this structure looks like this form, where c is a constant of integration, let's find p, q, and r where they are specified as being integer values. Once again, the controlling feature of the problem is right here. So you want to let u be equal to the x squared minus 1. So you've neutralized the cubic component. You could, of course, expand this, even using a Pascal's triangle concept, and get a rather long polynomial after you distribute the x. Definitely not the way to go, and would not impress an IB examiner. So given you've made that choice in terms of the x squared minus 1 controlling feature of the binomial piece here, well then you can differentiate u with respect to x. That's quite straightforward. Split the operators, and once again this precious x dx piece, here it is here, the x dx piece has value. It's exactly equal to 1/2 of the du. So you put the pieces together literally by substitution. This piece here, of course, is going to be, in terms of its future, your u cubed, and then this x dx piece that has already been established as 1/2 of du. I've already pulled the 1/2 through, so here we are with a rather simplistic problem now, an integral in terms of u, which of course is just traditional in terms of applying that straightforward algorithm. So you've got 1/8 of u to the 4th plus c, back substitute, so the net result of this integral as requested up here looks like it's going to be 1/8 of this binomial raised to the 4th power, and so hence we have p is equal to 1, q is equal to 8, and r is equal to 4. Pretty straightforward stuff. Finally, let's take a look at another example. Let's say you're given a rate function, or the derivative looks like this. Let's find the function itself, given some initial condition has to be met. So this is something that will always come in late in the game to help you basically find the constant of integration. So again, you might start to see a little bit of a pattern emerging. And again, if you switch over from this kind of notation into, okay, let's actually integrate this because that's what we need to do to anti-differentiate it to get started. The power of the notational form using the integral symbol and introducing a d to the d of x, the dx differential operator here will actually be quite powerful potentially. So there is, once again, this kind of linkage, and hopefully you're seeing that pattern I referenced a second ago. The controlling feature here is going to be this guy here. So if u is actually equal to x squared, you can then safely differentiate u with respect to x. You can already think in terms of splitting the operators to save a little bit of time. So du is actually twice dx. Once again, this precious package of x dx wants to be exploited as 1/2 of du. So this integral, for as slightly involved as it looks, reduces to, first of all, that 2 could actually come through, and then the x dx piece is the 1/2 of du, so there it is sort of pulled apart, and basically the integral of sine u du, really straightforward stuff, just looks like it wants to be the negative of the cosine of u because of the nature of how the cosine's derivative is negative to sine, so you can see the adjustment there. So we have this plus c, which of course you can't forget. So it looks like this integral is equal to this plus c, but this is trying to be the function in question because we're working backwards from the derivative. And so if f of x equals negative cosine of x squared plus c, let's meet the initial condition. So when x is 0, it looks like y has to be 1. And so careful here, of course, because cosine of 0 is 1 squared, and then you've got this negative nested in front, so it looks like c wants to be 2, so there's our final result. So final one that actually extends us a little bit more later on this. What about something that looks like this form here, namely the integral of d theta tan theta? Well, tan theta is better known as sine over cosine. One way to attack this problem is to look at it from that particular perspective, which is of course equivalent to what you see here in terms of the algebraic equivalency. So that's sort of mapped out for you here in terms of division by a fraction being multiplication by its reciprocal. So the controlling feature, as it turns out, and we'll see more of this later, will be the denominator. So let's let u actually equal that. Then du is actually cosine theta d theta, and that's directly relating to this piece here. And this is moving us towards something I'll come back here in terms of a view in our formula booklet. So if the derivative, as it turns out, of ln x looks like 1 over x, then of course the integral of this guy brings you back, and that's specified here. So this is moving us towards something that is a little bit new. Whoops, sorry about that. So the integral of sort of 1 over u du will be ln of absolute u, because we have to be a little bit careful about absolute value here in terms of the natural log function is not allowed to act on a negative value, plus c. So by back substitution, we end up getting this kind of form here. We will see more of this as we develop, that a plus c, some arbitrary constant, can just as easily be thought of as the ln of something. And then if you've got ln a plus ln b, you might be asked to consider something in this form here. Again, this example 4 bridges us to what's coming a little bit later. Hang in there. Good luck. That's it. Thank you.